All right, so here's question 2 of homework 6. We're doing similar stuff to question 1, so we're doing more truss analysis. And in this one, we're given something like a bridge. So it asks us to find the forces in members AD, CD, and CE. So that's right here, AD, CD, and CE. And then it gives us these load values here so that we can solve for this. So right off the bat, it would be helpful to find the reaction force here, because we know we're going to have to look at this free body diagram. So what I'm going to do is I'm going to draw a free body diagram of the entire bridge. And so I'll start off defining my coordinate system. So counterclockwise moment, x and y directions, and then I'll draw a free body diagram for the entire bridge just as a rigid body. So we have points B and K there. And then the other important points are this D and G, and then A over here. So we can add the loads that it gives us, P1, P1, and then P2 off to the side here, pulling on the bridge. And then the reaction forces are going to be, for point B, it's a roller, so it doesn't constrain it in the X direction. It can move in the X direction. But if it tries to move in the Y direction, it will actually push back up. So there will be a reaction force in the Y direction, BY. And then K is a pin, like in question 1. So it'll have both an X and a Y reaction force. Like this, K, Y, K, X. And then what we can do is we can take the moment about K, and that cancels out both of these reaction forces. And that allows us to isolate BY and look for that. So if we write out that equation, moment about K equals 0. I actually forgot to add the distances here, which are going to be needed. So I'll draw that out. All of these are 15 feet. And then up here we have 8 feet. Okay, so for moment about K, we have this P1 with 15 feet moment arm, this P1 with a 30-foot moment arm, and then this P2, if we look as it goes back here, it has this 8-foot moment arm, and then BY is going to have a 45-foot moment arm. So we can write that out. These will all be counterclockwise, so they'll be positive. So we have 15 feet times P1 plus 30 feet times P1, and then plus 8 feet times P2. And then our BY is actually going to push it in the clockwise direction, so that will be negative. So negative 45 feet, BY. And then if we just rearrange using algebra for BY here, we will get that our B force is equal to 6.6 kips. Then we can also just use sum of forces in the X direction and Y direction to find the K values. So in the X direction, it's just negative P2 plus KX. So we get KX minus P2 equals 0. And if we just rearrange that a tiny bit, we get KX equals P2. And P2 is given, so we have 9 kips. And then sum of forces in the Y direction allows us to find KY. So we have plus BY minus 2P1. So we have this, 2P1, and then plus KY. If we rearrange that, we get that KY is equal to 3.4 kips. All right, so from here, we should look how we'll actually find these forces inside the members here. So since we're looking for this member, these 3 members, we want to section it off between those members. So if we cut it there, we'll get a free body diagram of this part of the bridge. So I'll draw that. We already have our coordinates defined up here, and we'll start with point B up to A, and then C over here. And that forms a triangle that is our free body diagram. And then there's also the members like this. but we don't have to draw those entire things. We just have to draw the endpoints so that we can find the directions. All right, so the forces that are acting on this free body diagram are the By reaction force and the P2 force going off in this direction. And then we also have the member forces here, FAD, FCD, and FCE. All right. And then what we can do is I'll also draw out the distances real quick, 15 feet. And then since this is the intersection point between two straight beams, we can divide this in half. We get that this is 7.5 feet. Same here, where we have 8 feet and then 4 feet. Okay, so to start off, we should take the moment about C, because that'll cancel out both FCD and FCE, and isolate our FAD to allow us to find it the easiest. So we can write out that equation. Moment about C equals 0. And then we have By with that 7.5 foot moment arm going in a clockwise direction, so that's negative By. And then P2 with this 4 foot moment arm going in the counterclockwise direction, so that's positive. Comes P2. And then FAD has the same moment arm, just going in the opposite direction. All right, and then we can use algebra to rearrange that and get that our FAD is 3.375 kips. Oops, drew that weird. 3.375 kips. And since that is going inward here from point A, we get that that is a compressive force. All right. So we found one of the forces that we're looking for. And then after this, we can isolate one of the other ones. So one way to do that is take the moment about point A. That isolates force FCD because FCE's line of action goes through that. By goes through that as well. And then FAD and P2 also go through that. So we can simplify this further, like in problem 1, by actually moving this along its line of action to point D. And then at this point, the X component goes through the pivot point and doesn't cause any moment. So the Y component is the only thing we have to worry about. So let's find the direction of the FCD so that we can isolate the Y component. So we have C to D. And then FCD goes along this. Nice. And then we know that it goes 7.5 feet here and then 4 feet up. So its direction vector is going to be 7.5 feet in the X direction, 4 feet in the Y direction, and then the unit direction vector is going to just be divided by the magnitude. Okay. And then again, we can just isolate the Y component. So we'll take that out of it into the moment equation. And we get moment about point A is equal to 0. And then the only one acting there is this Y component of FCD. So we get a counterclockwise moment and then the moment arm of 15 feet. Okay. And then from here we can just simply divide everything over to the other side, and we actually get that FCD is equal to 0. Oops. All right. And then we only have one more force to look at, so FCE. And we can do that by taking moment about D, which cancels out FCD, FAD, and P2. So we only have to worry about FCE and BY. And we can do the same trick as before, move this along its line of action. And then we realize that the only force causing moment is the X component. So let's find the direction of that. And we actually know that this is flipped from FCD. So it's the same exact triangle, but it's just going in the opposite direction, in the negative y direction. So the direction vector is just going to be the same values with a negative y component. Oops. And then our unit direction vector, again, is just divided by the magnitude. All right, and then we only need the X component in this one. So we'll isolate that and write out our moment equation. So moment about D is equal to 0. And we have By going clockwise, so negative with a 15-foot moment arm. And then counterclockwise from this, which is an 8-foot moment arm. And we have 7.5 feet divided by the magnitude, FCE. Then using algebra, we can isolate that. Oops. And we get that FCE is equal to 14.025 kips. And this one is pointing outwards from the member, so that one is in tension. And there you go. Solved problem 2.